Hey, grade 10. So in this lesson, we're going to go over properties of sinusoidal functions. As I mentioned already, I'm hoping everyone did lesson 2, which was more of an activity where I wanted you to just graph out the sine and cosine functions. And hopefully you did that already, because if not, then this lesson might not make sense, at least at the very beginning of it. So we're just going to generally talk about what the main properties of sinusoidal functions are. And then specifically, we're going to look at some word problems later on. So again, learning objectives for today, make connections between the sine ratio and the sine function graph and this cosine ratio and the cosine function graph. Then we're going to look at key properties that they have. So first of all, how are the cosine graphs and the sine graphs created? Well, you might have noticed that in the sine graph, what we were really doing was observing the vertical distance or the height from the x-axis. And we do this because, again, when we go back to, and again, you don't need to know why this was created, but I think, in my opinion, I think it helps you make more sense of this, right? So this all comes from the fact that we are rotating around a unit circle that has a radius of 1. So if you recall, the very beginning, this is in unit 5, we talked about how the sine ratio around the circle. So if I have a circle like this, and it doesn't have to be a unit circle, but oops, that's a really bad circle. Let me just do that again. Where the center is at, there we go. So we said if we had a unit circle where the center was at, let me just change the color, was at the origin there. So if we had a point X, Y on this circle, you hopefully remember that the horizontal distance from the origin and the vertical distance from the origin, Y, and the radius had a special relationship in that because we have a right triangle right here, we can tell using Pythagorean theorem that x squared plus y squared equals the radius squared. So we hopefully remember that. And then specifically, we remember that if we have a related acute angle right here in this corner, the sine ratio is really just looking at the opposite over the hypotenuse, which in this case means that for the sine ratio of that related acute angle, it would be y over r. We're simply comparing the y coordinate over, we're comparing it directly with the radius of 1. Now, the nice thing about this is that when the radius is equal to 1, what happens is this simplifies even more. If the radius is equal to 1, then really we just have y divided by 1. And then that means that we end up with y sine theta is equal to y. And that's our y coordinate of the point as we move along the unit circle there. We could also create the cosine function by simply observing the horizontal distance from a point from the y-axis. And this is really just looking at the x-coordinate. So of a point from the y-axis. And so what we are doing there is we're essentially just looking at the x-coordinate as we move along a unit circle. And again, because it's a unit circle, when it is a unit circle, you can simply let the radius equal 1, which means that this becomes cos theta is equal to x. So that kind of makes sense with our last graph. And again, I hope you did lesson 2 already. As I mentioned already, if you didn't do lesson 2, then this might not make a lot of sense, but I'm basically just summarizing where these graphs came from. So I want to actually visually show you what is happening here. So if you click on this right here, I just want to show you this little visual I found here. So if I start off at 0 degrees, this is 0 degrees right here. I can see here that the sine function, as I mentioned already, is really just measuring out the vertical distance from the origin. So when I am at this first point at 0 degrees here, I can see that vertically, how far am I from the origin? Well, I'm just 0 units away. And then of course, now my vertical distance from the origin is going to increase, right? So I can see here, I start off at 0. So look at the green line there. Start off at 0, and then I increase up. And notice what's happening on the graph on the left-hand side. We can see here that as the vertical distance increases, so does the graph on the left-hand side. So I can see here that at around 90 degrees, at the 90-degree mark right there, and you can see it's 90 degrees because we create a right triangle there. We notice that the vertical distance from the origin is at its maximum point, which is 1. So we're 1 unit away from the origin. And then what happens as we go past 90 degrees? Well, now our vertical distance from the origin is actually decreasing. And then it decreases so much so that it actually ends up going to 0. So we see here that 180 degrees, the vertical distance from the origin is actually 0. And then what happens over here? As I go down, towards 225 degrees approximately, I can see here that my vertical distance from the origin, from 0, 0, is now negative because it's below the x-axis. And that makes sense. Now on my unit circle, I can see I'm below the x-axis, which means on my graph of the sine function, I'm also below the x-axis. And we continue this on, and I notice that at 270 degrees right here, I end up with a vertical distance from the origin that is -1. So now I am the furthest, that's the minimum point on my sine function here, because that's the lowest that I can be below the origin. And then I can see here that, of course, as my angle increases to maybe about 315 degrees or so, I can see here that now we are going back up. We are increasing, sorry, we are decreasing our vertical distance, which really means that we're going from the vertical distance is getting closer and closer to 0. And of course, once I reach 360 degrees, I am now back up at vertical distance of 0, and this continues on here. So I hope that kind of makes sense. The sine graph is basically, the sine function is really coming from, the sine function graph, sorry, is really coming from looking at the vertical distance from the origin. That's really all we're doing there. So I'm hoping that kind of makes sense so far. Now, the sine graph, when we can look at the sine graph over here, just going to open up another graph here. We can see here that for the sine graph, if we have, I'm going to list the angles off, it's going to be easier. Now, I want you to focus all your attention just on the blue graph there, okay? Don't worry about the green graph or the gray graph, because that's for tangent, which you'll learn about in grade 12. So I can see here that at the very beginning, at 0 degrees, again, we talked about this, the cosine, the cosine ratio tells you the horizontal distance from the origin, 0, 0. So first of all, at 0 degrees, I can see the horizontal distance is 1. At 30 degrees, I can see here that it's gone down to 0.86, and then it keeps going down as I move forward towards the 90 degrees. And you can see that on the graph to the right, what's happening is we start off at a high, at the biggest maximum, the maximum distance from the origin, which would be 1. And then, of course, we are decreasing as we move along the circle from 0 degrees to 60 degrees. We can see here it keeps going down. And then, of course, at 90 degrees, what do we notice? Well, 90 degrees, we can very clearly see here that the x-coordinate would be 0, which means the horizontal distance from the origin is 0. And then what happens as we go towards the second quadrant? Well, now we notice that our horizontal distance from the origin is now negative, because we are now to the left of the y-axis. So because we are to the left of the y-axis, the x-coordinate is now going to be negative. And again, this kind of goes back to the castle, right? We talked about how cosine is positive in the first quadrant. And then, of course, in the second quadrant, 90 degrees to 180, it makes sense that our cosine ratio would be negative. And of course, we see here, because it's negative, the graph is now below the x-axis on the right. And then, of course, at 180 degrees, our horizontal distance from the origin is also going to be at another peak, or in this case, a trough. It's going to be at -1, right? That's the lowest point that we have on the graph so far. So we can see here that the horizontal distance from the origin is -1. And then, of course, as we continue on, we notice that 210 degrees, 225 degrees, 240 degrees, what's happening as we move on to these angles here? Well, I noticed that the horizontal distance is now increasing, right? So instead of me going from, I'm going from -1 and closer to 0 now, right? I'm getting closer and closer to the origin. And of course, at 270 degrees, I am once again back at an x-coordinate of 0. And then, of course, after 270 degrees, I can see here that my horizontal distance from the origin keeps increasing until we go back to the maximum horizontal distance from the origin, which is at 1 at 0 degrees, or 360 degrees there. So I hope that kind of explains where these graphs are coming from. And I personally think there's a couple of visuals I've given here, and I really hope that you take the time to actually look at them, because I feel like they're again, if you're more of a visual learner, I think this is a great way for you to visualize. Sorry, I accidentally pressed on share. There we go. It's a great way for you to visualize what is really happening with the cosine and sine graphs. So again, just to give you another illustration, if it helps here, for the sine graph here, I can actually take this this button here that represents the degree, and I can see what's really happening here. That all I'm doing is I'm measuring out what the vertical distance is from the origin, and I can see here that as it keeps increasing, it essentially makes the graph, the sine graph, also increase. Then it seems to decrease at 0 degrees, and actually you can see the whole graph there. It seems to starts to decrease until it gets to 180 degrees, and then it keeps going past 180 degrees, 270 degrees. We can see here we reach the maximum, sorry, the minimum distance, sorry, the minimum y coordinate, which is going to be -1, and then of course we continue this on until we get back to 360 degrees, where it has a y coordinate of 0. And likewise, we can also see another kind of simulation that shows you how the cosine graph is created. And again, it's created the exact same way. We start with 30 degrees and we continue this on. And we can see here in this case, we're just measuring the horizontal distance, which increases first, and then it starts off high at 1, then it decreases, and then we can see here that it keeps decreasing. Obviously, the horizontal distance is decreasing, but then after 180 degrees, it starts increasing again until it completely goes back to its maximum height at 360 degrees, right? And that's basically how the cosine graph is created as well. So again, those are just good illustrations. I personally like seeing that. It's just a good visual of how these two graphs are created. Now let's go back to this. So our sine function graph, I hope you remember what it looks like roughly. If you look at the solutions, we had lots and lots and lots of key points, and very specifically, what we had to do was a little bit tedious, is find out what the sine of 30 is, sine of 45 degrees, sine of 60 degrees, 90 degrees, and so on, all the way up to 360. And then of course you need to do that for the negative angles. I would not expect you to do that for every single graph that we do. That would take extremely long. And there's no point in trying to memorize all those different points that were on the table of values in lesson 2. That was a very long table. You do not want to have to memorize that or even have to do it from scratch. So what we do is we focus our attention on what we call key or significant points. And the sine graph has 5 significant or key points. And these are the points that you really, really have to memorize and understand and know exactly where they are on the graph. This is very similar, and I'm going to make that connection with quadratic graphs. When you first learned about quadratic graphs, then we did transformations. Remember I said, remember the key points on the graph of y is equal to x squared, right? So I asked you to remember the origin, 1, 1, 2, 4, and then of course I asked you to remember some of the negative ones. So we had -1 and 1, and then of course I said -2 and 4, right? So I asked you to memorize a couple of those key points. So it's a very similar concept to this. And I'm asking you just to memorize these key points because what you can probably predict what's going to happen after this. In the next lesson, we're going to talk about transforming these graphs. So these are the 5 key points. It's 0 degrees and 0, and that is at our equation of the axis of the curve, which I'll call EOA. Equation of the axis of the curve is the EOA. 90 degrees and 1 is our next significant point, which is our maximum. So 90 degrees and 1. And then we have another significant point, 180 and 180 degrees and 0. Then we have 270 degrees and -1, and then that's our minimum point. And then of course we go back down, back up to our equation of the axis of the curve, which is 360 degrees. Sorry, equation of the axis of the curve is EOA. Sorry, just wrote that wrong. Which is 360 degrees and 0. So those are the 5 significant points on your sine function. And again, if you're kind of wondering, what happened to the points in between? It's not that they're not important, but to be quite honest with you, we don't want to focus on all the small little details and memorizing it all. You can definitely, I think some of you already started to remember it. I think some of you already figured out that, this is 30 degrees and 0.5. The next one, I think, and again, depends how much practice you had with this. For 45 degrees, we had a y coordinate of 0.7 approximately. For the next key significant point, it was 60 degrees, or significant angle, sorry, I should say. It was 0.87. And then we obviously had a y value of 1. That's supposed to be 0.87, a y value of 1 when the angle was 90 degrees, and then we continue this on. So you can obviously remember some of these key points, but I would say the focus is on the 5 points here. And this is extremely important. I want to make a note about this. Whenever you draw your sinusoidal function, please do not do something like this. So sometimes people will do the key points, and for some reason, they think that this is acceptable to just connect the lines like this, like a straight line. No, you need curves, right? And I know I sound picky about that, but the reason you do the curves is because, again, I don't want to get into much detail about this, but when you learn about continuous graphs later on in grade 12 math, you're going to notice that you have to make this a continuous graph, right? And we know that these, one of the definitions of these sinusoidal functions is that they have smooth symmetrical waves. So we do have to actually make it look more like a wave, right? If you make it straight, that basically you're almost implying that it's a straight line in between, which is not the case at all. We can see here that this is definitely not a straight line. If it was a straight line, it would increase proportionally, right? And that's actually why I made a point of saying that this point right here, that a lot of people get confused. They think that this would match up with 45 degrees because it looks like it, right? You would think, oh, 0.5, it's between 0 and 1. And because the sine ratio at 0 degrees is 0, the sine ratio at 90 degrees is 1, you would think that the sine ratio at 45 degrees would be 0.5, but that's not the case. It actually belongs to 30 degrees. So again, if it was perfectly proportional, this would actually be at 45 degrees right here at the 0.5, but that's not the case, right? We can clearly see it doesn't go straight through it like that, so it's symmetrical. So I'm hoping that makes sense. Again, really, you just have to memorize those key points. I cannot say that enough. Cosine functions. So the cosine function is extremely similar. Actually, we noticed that it has the exact same maximum point. The maximum point was 0 and 1, and the other maximum point was 360 degrees and 1. We noticed that it also has a minimum value of -1 and 180 and negative 180 degrees and -1. But we noticed that we reach the same points, but we just reach same y values, but we reach them at different angles, right? So our key points are the maximum at 0 and 1, 0 degrees and 1, which is our starting point. Our next point is at 90 degrees and 0. Then we have 180 degrees and -1, 270 degrees and 0, and 360 degrees and 1. So if we look at the graph side by side, so I put these two together in the same Cartesian plane because I want you to kind of look at this and tell me what's similar, what's different about them. Well, the nice thing about it is that the sine graph and the cosine graph have a lot of things in common. They have the same amplitude, the same equation of the axis of the curve, EOA, and the same period and the same maximum values. What's the one big difference that I noticed? Well, they basically seem like the same graph. What's the only difference? Well, it just seems like this cosine graph is simply the sine graph shifted 90 degrees to the left, right? Which is hopefully reminding you of transformations. And we're going to talk about that. We're going to get to transformations and you're going to notice that they have a lot in common, right? Really, the sine graph and the cosine graph are almost one graph together, because really the only difference is that the sine graph has simply been shifted 90 degrees to the left. Or the other way you could look at this is start with the cosine graph and then say, hey, wait a minute, it looks like the sine graph it's just been shifted 90 degrees to the right from the cosine graph. So it depends which perspective you're taking. If you're looking at the sine graph as your starting point, then you could say that the cosine graph is simply the sine graph shifted 90 degrees to the left, or you could say that the sine graph is the cosine graph shifted 90 degrees to the right. So here are the main properties of the sine and cosine graph. And you're going to notice that when you're copying this down, I would not even bother repeating this part. The 4 main properties there are exactly the same for both. So what is really, really important for both of them? Well, they both have an amplitude of 1, a period of 360 degrees, because the cycle starts and ends at it starts at 0 degrees and ends at 360 degrees for both of them, right? So obviously the difference between 0 degrees and 360 degrees is 360 degrees. The equation of the axis is y is equal to 0 for both of them. And again, why is that the case? Well, if we go back to our graph here, just want to make sure you see that, you can clearly see here that the horizontal line that goes right between the maximum and the minimum, so the maximum of 1 and the minimum of -1, so the horizontal line going straight through them is 0, right? We can see here that the period, as I mentioned already, is 360 degrees because it starts at 0, 0 for the sine graph and ends at negative 360 degrees and 0. And for the cosine graph, you can see here that it starts at 0 and 1 and ends at 360 degrees and 1. So there's another cycle as well. So we know the period is 360 degrees, just looking at a couple of cycles. The amplitude is 1, because that's the distance from the equational axis of the curve, and the max and the equational axis of the curve and the min. And the domain and range is the same for both of them. So the domain is XCR, because I can sub in anything into my trig function. I can find the cosine or sine ratio of any angle, but my range is limited. My range is limited in that I can only go from -1 to +1. And we already saw that on the graph. We can't go any lower than -1, and we can't go any higher than +1. And the zeros or the x-intercepts, if you recall that word, or the root, sometimes it's called that, but that's more when we're talking about an equation. So the x-intercepts are basically where it hits the x-axis, and we can see here that in the first graph, the sine graph, it was 0, 180 degrees, and 360 degrees. And of course, you can continue this pattern on. What are we doing to find each of the zeros? We just add 180 degrees each time. And then, of course, for the cosine graph, as I mentioned already, I wouldn't even bother writing this down, because we get the exact same properties. We have an amplitude of 1, a period of 360 degrees, an equation of the axis of the curve that is y is equal to 0, and a domain XCR and a range YER such that it goes from -1 to +1. And the only difference really that we can notice right away is that the zeros are different. It goes from 0, 270 degrees, and so on. And you can pretty much predict what's going to happen. You simply keep adding 180 degrees to find the next 0 after that. So the zeros occur at different spots, and we can go back to the graph and compare. So we can see here that the x-intercepts, for the sine graph are at 0, 180 degrees, and 360 degrees. Let me erase some of this. It's getting really messy here. 0 degrees, 180 degrees, and 360 degrees. And then in blue, for the cosine graph, we can see here that our zeros are at -90 degrees, 90 degrees, 270 degrees, and of course the next one is 450 degrees. So we're essentially just adding 180 each time to get to the next x-intercept. So I hope that kind of key properties that we have for the sine and cosine graph. Next thing I want to talk about is the significant points on your sine graph. This will make a bit more sense when we talk about the word problems, but I want to introduce it to you now. So the significant points on the graph will basically split up your graph segment that we have is from the equation of the axis of the curve, and sometimes for short form, I'll call it the middle, especially in this sense. Okay, I'm going to call it the middle one. That's not the formal name, just so you know, but if I talk about the middle point, it's just an easier way for me to kind of remember the equation of the axis of the curve, or I can of axis. So it's split up into a couple of different parts for a sine graph. So equation of the axis of the curve to the max, and then it goes from the maximum to the equation of the axis of the curve, EOA, and then from the EOA to the minimum, and then from the minimum to the EOA. So it kind of goes middle, max, right? So if you kind of draw this out, middle, max, max down to middle, middle down to minimum, and middle back up to the middle. Sorry, minimum back up to the middle, right? That's kind of what the graph looks like, right? So what really happens is when I draw this out, it's actually split up into 4 separate parts. There's a first segment that goes from the middle to the max. There's a separate segment that goes from the max. Oops, I went too far there. That goes from the middle point to the minimum. And then, of course, we have the last segment here that goes from the middle to, the minimum point to the middle, right? Back up to the middle. So it's kind of split up into 4 separate parts. And again, you're probably wondering why this is significant to us. This is going to be important for us to understand that it says, went from the maximum point to the minimum point. You can already see here that what happened is you went from the max to the minimum, which means that you technically have covered ground. You technically have passed by 2 different segments of the graph. You passed the maximum to the middle and the middle to the minimum, which means that you have gone through half of the whole entire cycle, right? So it's going to be really important for us to understand that. Again, this is kind of aware of that, okay? And the cosine graph can be split up into 4 segments. The only difference is that the order is going to be slightly different. So I can even show you what it looks like for the cosine graph. And the cosine graph, it goes, let me do a different color. So the cosine graph, it goes max to middle to minimum to middle to the max, okay? And then what we see here is that the resulting graph that goes max to middle to max can then be split up into 4 separate segments. So we have this one right here. That's the first segment. Then we have the next segment, middle to minimum. And then we have the minimum to the middle point. And then, of course, we have our last segment, which is the middle point to the maximum, right? So we have 4 separate segments. So I personally find it easier to think of it as to break the cycle for separate parts. So that if you're given a word problem and you're told, we went from the middle point, sorry, the equation of the axis of the curve to the minimum point, then you can already see that would be 1/4 of the way. Does that kind of make sense? And again, I think this will be a bit more clear when we look at word problems, and we'll look at some word problems later on. So the entire unit is called sinusoidal functions. So you're probably wondering, what does that actually mean? Well, sinusoidal functions are basically periodic graphs, so they're still periodic. So remember, it's the same definition as before. That means that they repeat in equal intervals, at equal intervals. So sinusoidal functions are periodic functions that can be transformed from the sine theta, and by default, we already talked about this, we saw this, the cosine graph is basically the sine graph just shifted. That's all it was. So because of the transformation of the sine graph, by default, the cosine graph is also transformation. So the name kind of throws people off because they think it only relates to the sine graph, but remember, it also relates to the cosine graph, because the sine graph and the cosine graph are essentially just translations of each other. They're not even transformations of each other, just translations of each other. And again, we're going to talk about transformations. We haven't got to that yet. So if in general, like obviously this is the formal, the first line there is a formal definition, but the next part is more of a general description of it. So if you ever look at a graph and you see that the general shape of it looks and it has smooth symmetrical waves, then you know it's going to be a sinusoidal function. So let's look at a couple examples and determine, is it periodic? And if it is periodic, is it sinusoidal? So really important that you understand, you cannot have a graph that is sinusoidal, but it's not periodic. And if it is periodic, then you then have to further check, is it sinusoidal or not? So by default, if something is not if it's not sinusoidal, then it's not going to be periodic either, right? So you first have to check, is it periodic? And if it is periodic, is it sinusoidal? So let's look at the first one. Is it periodic? Well, I can tell you right now, it's definitely periodic. And we did this in the first lesson because we know that we have repeating y values, right? So I can see here that this would be one cycle. So there's one possible cycle. Another possible cycle I could look at where the y values repeat is something like this from the middle and then back down like this. And then it kind of repeats, right? So there's another cycle I could look at, right? So I definitely have repeating cycles, right, that happen in equal intervals. So this is definitely periodic. So periodic, yes, definitely periodic. Is it sinusoidal between them? Or basically another question to ask, does this look like a sine function, right? It comes down to that. Does it even look like a sine function? Yes, it does. It's definitely periodic and it's definitely sinusoidal, right? And I hope you can see why it's periodic, even though, and if it started at the origin, and then you might be thinking, well, I thought that all the graphs had to start at the origin for them to look like the sine function. But remember, they don't have to start at the origin. They could have started somewhere else. But the main thing is that it still has the general shape of the sine function. The next one, sorry, I get answered too quickly there. The next one throws people off a little bit. So it definitely has the waves, right? We see the waves, which makes us think, maybe it is symmetrical. You might think it's periodic just of the way it looks, but it's definitely not periodic because we can see here that there is no cycle that repeats over and over again. I mean, you could say that there's a general pattern that repeats over and over again, but it doesn't repeat by the same distance because it keeps getting higher and higher and higher. So this is definitely not periodic. So the fact that it's not periodic, you kind of already answered your other question. Is it sinusoidal? Well, it definitely can't be sinusoidal because sinusoidal not sinusoidal. It's actually neither, right? So we say neither. Last example here. Is it periodic? Well, let's check the first thing. Is it, sorry, I'm just turning up the one there. So we can clearly see here that this is definitely periodic because it does have a cycle that repeats. So for example, that's one of the cycles that let me go all the way. This is one of the cycles I could have. And then of course I could repeat this again. And again, this is just an example, one cycle, but it shouldn't be blue. Here's another cycle. So it kind of goes there and it goes back up to kind of the middle right there, roughly speaking. So I can see here, actually, the one is off a little bit. But anyways, it's not going to be perfect, but I kind of made a mistake there. But this is my other cycle that repeats over and over again. So this is definitely periodic. I know that for sure. And the question is it sinusoidal? And this, even though it has the waves, right? And this is what throws people off. You might look at that and be like, doesn't that look like the sine function? No. The sine function, remember, has to be symmetrical like this. It has to go like that, go back up, down. So this is actually not symmetrical waves. They're obviously not all the same. Like if you look at the actual wave part of it, they're not all the same. Whereas a sinusoidal function would have all the waves the same if it continued on, right? They'd all be about the same. The last one there is periodic, but it's not sinusoidal. So I hope that kind of makes sense so far. And then of course, as I mentioned already, the middle graph is neither. So a couple of properties of sinusoidal functions. The good thing about this, and again, I wouldn't even bother writing this down because all three here the first three, we already discussed, and they're actually all properties of, I'm just going to use a highlighter. the first three here are actually all properties that we already discussed, and they're all properties of periodic functions. So because sinusoidal functions are also periodic functions, they have the exact same properties, right? So they have a period, which is the length of a complete cycle. They have an EOA for short form, right? So they all have the EOA, the equation of the axis to the curve. They all have an amplitude, which is distance from the equation of the axis to the max, and the equation and distance from the equation of the axis of the curve to the minimum. And the phase shift is the one new definition here. But again, we're going to talk a little bit more about this with the transformation has moved from the y-axis. So in this case, if I decide to start this cycle right here, then the phase shift is just how far did I move from the y-axis, right? But that's going to change depending on where you start. And we'll talk a little bit more about the phase shift later on. So modeling problems using sine functions. So whenever you look at a word problem, whenever you're looking at a real world problem, and you notice that there's some sort of periodic movement that happen in equal intervals. So it's, in other words, there's a predictable pattern with it. You can essentially model problems using the sine or cosine function, right? Again, really important. You has to make sure that you actually see periodic movement, and it has to kind of happen in symmetrical waves, right? So an example of that, we talked temperature is definitely sinusoidal because we know that we can start from our middle temperature. Think of it this way: we can start from the spring where it's maybe rainy, it's not too warm. Then it goes to our maximum weather when it's hot, and then it goes back down to the middle, which is autumn, where it starts getting a little bit cold, and you have to start getting your coat again. And then, of course, from the middle temperature, we can go back down to our lowest temperature, which happens in winter. And then we go back up to our middle temperature, which would basically be spring again. About that temperature, it would create a smooth symmetrical curve if it was, for the most part, predictable weather, right? Whenever the question mentions radius in a word problem, then they're usually referring to the amplitude. And a good example of amplitude, I always like to bring this up. If you actually think about volume or noise, the amplitude of that noise is, it's really just asking how far from the base sound is it, right? So the radius, whenever the question brings up anything to do with radius, which essentially measures how far you have moved from the middle line here, that's essentially looking at your amplitude, right? Because really amplitude is just measuring what is the distance from the equation of the axis of the curve to the max, and what is the distance from the equation of the axis of the curve to the minimum. That's really what amplitude is. Okay. So any question that deals with, radius or, distance from the center, that's going to be your amplitude. If the question brings up how long it takes to do a full rotation or revolution, it refers to the period of the function. So that's basically how long does it take to go all the Ferris wheel, whatever it might be, right? That's referring to the period. The axle or the midpoint, that refers to the equation of the axis of the curve. So if I ever have a question where, we're looking at propellers or even a Ferris wheel, and then we're talking about the center of it, and it says how far from the center is it? Well, really it's just asking if it tells you how far it is from the, how far up the center of or the midpoint or the looking at the equation of the axis of the curve, right? That's basically the middle point there. Anytime that there are a few questions where they'll do this, and again, I wouldn't worry too much about this, but if the question ever asks you to find the horizontal or vertical distance of a point on a circle, so let's say you have a circle here, and it's simply just asking you how far vertically or horizontally a point is. So maybe it asks you for the vertical distance or the horizontal distance. It's just asking you how far is that from the origin. Then you could actually use these two equations here to figure that out. You would simply look at the radius of the circle and the degree of the circle at that, but the angle is for that point on the terminal arm, right? So if you have the angle and the radius, then you can easily find the x and y coordinates for that point. Again, that doesn't come up as often, but there are a few questions where they will basically tell you, you move 30 degrees around the circle that has a radius of, 5x and y components. You would simply use this formula there. Okay, so I hope that kind of makes sense so far. And the last thing I want to talk about is any questions that deal with speed or, how fast something is moving. If it ever asks you for speed, you want to remember the formula for speed. You actually learned this in grade 9. Speed is distance over time. So if the question is saying, how long does it take to do one? How fast is the Ferris wheel moving, or how fast is that ball moving, or how fast is it rotating around? Whatever the question might be, a lot of times it will have to do with how far you have moved divided by how long it took you to move all the way around. So in this case, you would have to do the circumference, because really circumference measures how long the distance is around, right? And then you simply divide that by how long it takes to go all the way around, which is your time. So you want to remember those two key points on the circle, and then the time that it takes to complete it is your period. And if you know that, then together you can find out what the speed is. And again, you might want to remember that circumference is 2 pi r, right? Hopefully you remember that from grade 9 as well. So let's look at a couple of examples. The water here is in terms of time. Discuss and interpret what the graph by identifying the period, the equational axis of the curve, and the amplitude. Okay, let's find the period first. So the period is really just asking how long does it take to complete one cycle. Graph here. I'm already automatically thinking of starting at the origin because it's easier to read the origin there. And I can see here that one of my cycles starts at 0 and ends at 3. So because it starts at 0 and ends at 3, that means that my period is going to be 3. And I hope that kind of makes sense so far, right? Now keep in mind 3 seconds. I could have started at a different point. So I could actually I could have started at the middle, at the maximum height, and could have gone to the next maximum height, the peak, right? Consecutive peaks. Now, if I did that, I would have to approximate this and say, okay, this is about, what would you say, 0.75. And this is about, what would you say here, 3.75. So just keep in mind that if I chose a different point where it is, right, I'm kind of approximating in this case, right? But if I had to kind of do a little bit of an approximation, I would say it is roughly 0.75 and then roughly 3.75 when it reaches the next maximum height. So I can see here pretty clearly, hopefully, of 3 seconds, right? So I hope that kind of makes sense so far. So my period is pretty easy to find. I know it's going to be 3 seconds regardless of what it is. The amplitude, I can actually, let's start with the equation of the axis of the curve. I always like to start with this one first. So there's 2 ways to find it. You can either do it visually inspecting the graph, and this is what a lot of people might prefer. So even at the very beginning of the graph, I think we could kind of see clearly that the horizontal line in the middle was going to be 2, because it seems to split that red in half. Now, one thing I always warn students about is, as much as you do it both ways. You can find the answer by visually inspecting the graph, or you can use the formula which basically tells you to take your maximum value and your minimum value and add them and divide by 2. You're just finding the average of the 2. So when I do that, max divided by min divided by 2, that ends up giving me a max amplitude. I can easily find the amplitude by simply finding the distance from the horizontal line to the maximum point, and then the distance from the horizontal line to the minimum point. And I can see here that by doing a little bit of math, the maximum height here is 2.4, as I mentioned already, and the minimum height is 1.6. So if I want to find the amplitude, I simply take 2.4 and I subtract 2, that gives me 0.4, or I can take my minimum height. So to find this one here, I take 2 minus 1.6, and I get 0.4. So kind of 2 different ways I could have done that, right? To find the maximum height, I could take, or to find my minimum height, I can take the equation of axis of the curve and subtract the amplitude, right? And either way, I would notice that is the amplitude should just be 0.4, right? So I hope that kind of makes sense so far. We could also obviously use a min and then divide by 2. So it's half the distance between the maximum and the minimum. So hopefully that made sense with that graph. So we were able to look at the graph and identify the properties there. And here's another question. Height of one tooth on the circular blade relative to the cutting surface with respect to time in seconds. So first question, how high above the cutting surface is the blade set? So to find out how far it is, when the blade is actually directly, but it's really saying, what is the initial height? And I'm hoping, because that's the height that you're setting it at, I hope you realize the initial height, just like we did before, is really just referring to the y-intercept. So the question is asking you, what's the y-intercept? So we look right here, we can clearly see the y-intercept is 1. So we say that it is set at 1 inch above the cutting surface. It's going to be our initial value there. So the second part of the question says, what is the period of the function and what does it represent in this situation? So the period is basically calculated by by finding one cycle and figuring out how long it takes to complete that one cycle. I believe the first maximum, or the initial starting point, to the next consecutive maximum. And I can see here that it would be a total of 0.04. So what does that represent? That just represents how long it takes for the blade to do one full rotation. So when we're cutting down on the cutting surface, the circular blade is rotating. And again, that kind of makes sense, right? It's not going to take that long unless something's wrong with your machinery there. It should be pretty quick, right? So it's going to be 0.04 seconds for it to go one full rotation around. The next part to look at is would simply be the distance from the center, or the horizontal line that cuts it right in half, and the distance from the center to the max, and the distance from the center to the minimum. So we can see here that the equation of the axis of the curve is going to be at -3. And again, don't let your eyes trick you. If you might get a little bit wrong if you just look visually. So a lot of times, for some reason, people think it's 4. Oops, sorry, I don't know what happened there. A lot of times people think it is actually -4. A is -3. And again, I would use the formula just to verify that that's correct. So I could easily find that by taking my maximum height, which is 1, and my minimum height, which is -7. And then you simply subtract them because you're finding the distance. It's, remember, amplitude is half the distance between the max and the min. So I need an amplitude of 4. And I could quickly verify that the amplitude really is half of the distance between the two of them. And sorry, I just want to check something because it's something weird with the formatting here. I think I might have. Yes, I did not mean to do that. I'm not sure why it kind of split off really weird. Between the maximum, it represents, sorry guys, not sure what happened there. Okay, I might have accidentally pressed something else. Okay. So that represents the distance between, half the distance between the maximum and the minimum. But in this case, in the real life context, what it represents is the radius of the blade, right? And again, that makes sense because that's how far we can go from the center, right? So we know that the center right here in this case, we were told is going to be -3. And so what we're saying is, what is the, so -3 is like right there. Let's just say it's -3. That's what it's set to. So we're just finding the amplitude, which is a total of 4, right? And that's going to be the radius in this case. And the last part of the question says, sorry, it's supposed to be a 4 there. The last part of the question says, what is the speed of the blade? So to find the speed of the blade, what we need to do is figure out for this blade. So I'm actually going to redraw this. So here's my blade. It has a radius of 4 inches. So what I want to do is I want to calculate how far, what the total, the circumference is, because the circumference is really just asking how far did the blade move altogether in one rotation. So the first thing I need to do is figure out what the circumference is, because that's my length around the circle. So to find circumference, I take 2 and multiply by pi, and I multiply by the radius, which is 4. So this actually ends up giving me 8 pi. That's going to give me what the circumference is of the circle. And then, of course, what I'm going to do now is I'm simply going to divide. So this is my circumference right here. I'm going to divide this by how long it takes to complete one full rotation, which is the period. So the time it takes to complete one full rotation, or to basically go around the circumference, is going to be 0.04. So my last step here, simply take 2 times pi times 4, which is 8 pi, and I'm going to divide this by 0.04. And again, if you have a calculator, just do that. But if you don't have a calculator, you could always simplify this a little bit more. Or you could do some mental math here. You know that 8 divided by 4 is 2, but since I'm dividing by 0.04, that would just be 200 pi. So I just move the decimal over 2 times to the right, and I write 200 pi. And if you put this in a calculator, you get approximately 628. I can't remember how many, or sorry, not meters, inches per second. And that's how fast the blade is going, which seems outrageous. You're probably thinking like, that's really, really fast. But again, it's a blade, right? So you want it to go that fast. You want it to be a quick movement because you're actually cutting it down, right? Bit of a trickier one. So let's read through it. So we have a Ferris wheel with a radius of 15 centimeters that's rotating around. You reach a maximum height of 32 meters after 6 seconds. And I'm going to highlight all the keywords here. 32 meters at 6 seconds, and you reach a minimum height after 22 seconds. And the radius is 15 meters. So what is the minimum height? And then how long does it take to complete one full rotation? So in this question, what I want to try to do is figure out, so what is the minimum height? And then I'm going to look at how long it takes to complete one full rotation. What I would start with first is drawing a picture, which I kind of set up for you by putting a little Ferris wheel on there. I did not draw it myself, so I don't take credit for that. I think I found it under one of the Desmos acting around. They're pretty happy, hopefully, or maybe not, because they don't like heights. I personally am not a fan of heights, so I would be terrified, but that's just me. So we're told that the radius of this Ferris wheel is 50 meters. So that means that the distance from the center right here to any point on this Ferris wheel is going to be 50 meters. So I'm going to use that to help me find out what the maximum height is. So first thing I realized is that because my maximum height is 32 meters, so I'm going to write down max height, or just max. I know that I'm going to reach this at 6 seconds. So I'm going to label everything I know. And I know that the maximum height here is 32 meters. So that means that the distance from the ground all the way up is a total of 32 meters. So what I'm going to do is use all this information to help me identify what the minimum height is. So first thing I hopefully notice is that because my radius is 50 meters, that means that my distance from the center to the maximum is 50 meters, but then the distance from the center to the minimum is another 50 meters, right? It's 50 meters from the center, or in this case, the equation of the axis of the curve up to the maximum is 50 meters. And then the distance from, and that means that the distance from the center of the Ferris wheel to the minimum point is going to be 50 meters as well, right? So we have 50 meters, 50 meters, perfect. So far, so good. So how can I use this to figure out what the minimum height is? Well, hopefully you realize that if this total of 30 meters that I have moved, so that means that if I want to find the minimum height, I can simply take the 32 meters and subtract off the 30 meters, right? I simply take away the radius twice, which is the diameter. So an easier way of thinking about that is you could have just said, well, I can just take away the diameter, and the diameter is 15 times 2, right? And that would have also helped me find the solution. So I know that the minimum height in this case, I'm going to put this at the bottom here, the minimum height is going to be 32 minus 15 times 2, which is 30. And then we're also specifically told that this minimum height occurs at 22 seconds. So I'm just going to write down everything I know. So I found the first part. I know because the amplitude or the radius is 15. And again, remember, amplitude is the same as the radius in this case. So what else do I know now? So I know the minimum height. So I got the first question answered. What about the second part? How long does it take to complete one full revolution? Well, when I ask you for one full revolution, what it's really asking you is how long does it take to go around the Ferris wheel fully? So I know that it took me 6 seconds. So if I'm on this Ferris wheel, all I know is that to go from the max to the minimum, it took me 22 seconds. So that means that this distance right here, from the max to the min, was traveled in a total of how many seconds? So I need to figure out how long did it take to go from the max to the min? Well, 22 seconds minus 6 seconds, that means it took me 16 seconds to go from the max to the minimum. And that would mean that for me to go all the way around, to make one full rotation around the Ferris wheel, it would take me twice as long because from going from the max to the min, I only traveled halfway. So that means that it would take me twice as long to go all the way around. So doing that math there, 16 times 2, what does that give you? 32 seconds. There's a different way I could approach this. I could also look at I could look at this graphically, right? If I want to put this on a graph, this might make a little more sense to you. So I'm told that at 6 seconds here, this is time. I'm told that at 6 seconds, and actually, let me redraw that. I'm going to make this a little bigger. So I'm told that 6 seconds here, I reach 22 seconds. Let me just label that. And sorry, I have a couple more things to label. This is 2 meters. This is 32 meters. So I'm told that at 6 seconds, I reach a maximum height of 32 meters. And then at 22 seconds, I reach a minimum height at 2 meters, right? The next time, for the first time there. So what I have so far is that the graph kind of looks like this, right? It kind of goes from a max to the minimum. Now, do you remember how we talked about how the cosine graph and the sine graph can be split up into 2 segments? Well, there's basically 2 segments as well. And if you see the picture, it's also clear as well. The equation of the axis of the curve, remember we said, is right in the middle. So the equation of the axis of the curve, or the middle line there, is going straight through the max and the min. So I know for a fact that we have crossed the equation of the axis of the curve right in between, right? So that means that really what we have is that we have passed through 2/4 of the graph altogether. Think of it that way. So I went from the maximum to the middle of the equation of the axis of the curve to the minimum. So if our cosine cycle is split up into quarters, then I really have passed through 2/4 of the 4. So that means I've only gone through half the graph. So in order for me to complete this graph, I would actually have to go twice the distance that I've already traveled. So far I've only traveled 22 seconds, 16 seconds altogether. So for me to complete this whole entire cycle, I would have to go another 16 seconds. So I have to add 16 seconds more to figure out how long that whole entire period would take. So what's 22 plus 16? We know that gives me 38. So that means that I wouldn't complete this rotation until I get to the 38 second after the start at the very beginning. So altogether, what do I see here? That means that it's going to take 32 seconds for me to go all the way around. So I'm hoping that kind of makes sense. So we know that to go from the maximum to the minimum, which is halfway through. So let me just erase this. I personally think it's easier to think of it from the Ferris wheel perspective. So if it took me 16 seconds to go from a maximum to my minimum, that's 16 seconds right there, then it should logically make sense that it's going to take me another 16 seconds to go from the minimum to the max. So this is going to be another 16 seconds. So that means my total time, or my total period, is going to be 16 plus 16, which is 32 seconds. And I hope that kind of makes sense so far. So it takes 32 seconds altogether to complete one full revolution. And that is it. So big conclusion here, guys. And again, those are a lot of these problems again. So it's not the only time you'll see this. You'll actually see different versions of that problem, just in a different context or slightly different wording. We're asking you different questions, but it's going to be a similar context there. So the good thing about these questions is if you understand. So big conclusions here. Sine and cosine functions, as I mentioned already, have a couple key properties that they have in common. The amplitude is 1, period is 360 degrees, equation of the axis of the curve is y is equal to 0. That's the midline there. And then the domain is x. And if a graph is periodic and it generally speaking has the same general shape of a sine function or a cosine function, because those cosine functions is a translation of it, then it is sinusoidal and therefore can be modeled by either sine or cosine. And always know which one it can be modeled with, the cosine or sine graph. You can technically use both, but sometimes it's easier to use one versus the other. And we're going to get more into that in next week's lessons. So that is basically it for now. And if you want to do the extra questions there, you will have to use Desmos to graph. So if you want to graph with Desmos, make sure that you change your setting by going to the tool wrench, the little wrench there, and then make sure that you put the correct settings. I would actually just use the ones I've kind of indicated here for you. Or if you click on this graph, there's already a sine and cosine function graph that you can already use. So you can just switch your A values if it's next time. They get kind of interesting. So it's kind of cool. And I think that's everything for now. So best of luck with the homework. Have a happy Easter and have a great week.